Given the complexities of the climate system and the complicated feedback loops that link its various components together, can the computer models we build hope to cope? Well, it turns out they work reasonably well, at least at predicting the past. Now, you may not be very impressed with predicting the past, but what we're talking about here is not just reproducing what we know happened in the past, but we're reproducing it with a model that includes all of the complexities of the climate system. These diagrams indicate that we're doing pretty well. In both cases, the black curves represent the actual temperature observed on Earth from 1900 to 2020, with the latter point being the black dot in the upper right-hand corner. You see the temperature more or less constant with a slight rise before 1960, and then the rapid rise that we've been talking about from the 1970s to the present. So the black curve is identical in both cases and represents reality. In the bottom case, the blue curves represent what the models predict. Now, there are about 16 of these global climate models around the world. They run on different machines. They were written by different scientists, but they all give roughly the same answer. And the dark blue line represents the average. And it represents the changes we would have expected based only on natural phenomena. You can see some of the natural phenomena labeled there, the large volcanic eruptions. So Agung in Indonesia, El Chichon in Mexico, and then by far the largest eruption over the last century, Mount Pinatubo in the Philippines in 1991. You see, the models predict that these eruptions lead to a sudden decrease in the Earth's temperature, followed by a slow recovery over several years. If you look at the black curves, you see, lo and behold, indeed, there is a decrease in temperature tied to each of these volcanoes. It's not quite as big as the models predict, and then it recovers again over a few years. But the dominant thing to take away from this lower graph is that the blue line predicts from 1960 to the present a slight decline in the Earth's temperature when only natural phenomena are included, whereas the black curve clearly shows a dramatic increase. The upper curve is exactly the same. In this case, the yellow lines represent the individual computer models and the red line represents the average. And you see the volcanoes in the same place with the same predictions. But what you see is that we've added in man-made effects. That is, we've added in the increases of all the different greenhouse gases that have been accumulated in the atmosphere because of human activity, and we've added in changes in land use like deforestation, which has also contributed to the change in the geochemical balance of the atmosphere. And you see that this model, run on the computer, matches remarkably well the temperature record over the last 120 years. So predicting the past may not sound impressive, but these models do a remarkable job when they take into account both the natural forces and the man-made contributions to climate change. Now, what does that mean about the future? The Intergovernmental Panel on Climate Change, a worldwide consortium sponsored by the UN of scientists who work on these problems, issues a report every 5 years, or in this case it's been 8 years, and they attempt to predict what the future will hold. To do that, they have to assume some model going forward for how much CO2 and other greenhouse gases we're going to pump into the atmosphere. So what do these predict about temperature? Well, we put this into the model and we extrapolate forward in time, and we see that even in the most optimistic scenario, the temperature from today will continue to rise by nearly another 0.5 degrees centigrade before it levels out and in 2100 begins to decline. The intermediate case sees a rise of another 1.5 degrees in temperature, and the business as usual cases lead to rises of 3 or even 4 degrees centigrade. The dot on there shows where we are. It doesn't look like we're on the optimistic scenario. We're on one of the upper two scenarios. Having seen the consequences for Earth of a 1 degree centigrade rise, a 4 degree centigrade rise is not something we want to contemplate. The models also agree with each other reasonably well, extrapolating into the future, and extrapolating as to what the temperature will be in different parts of the Earth. So in the center, you see the 2020 to 29 maps, and in the right-hand side, you see the 2090 to 2099 maps, so 70 years into the future. You see in all cases, the models predict that the continents warm more rapidly than the oceans, and in all cases, you see that the high latitudes warm more dramatically than the equatorial latitudes, and in particular, going towards 2100, we see enormous rises of 6, 7, or even 8 degrees centigrade, 15 degrees Fahrenheit in the northern regions of the Arctic. And here's what we actually see today. Here's the measured temperature in 2018. Again, you see the continents are warmer than the oceans, and the high latitudes are warming most of all. Now, how confident are we of all these predictions? Well, we can look around us, take measurements of what's happening on Earth today, and see if we can see signs of foreshadowing. Here we have Greenland's ice cap in 1992 and 2002. Greenland is covered with a thick layer of ice, 2 miles thick in most places, and it's covering an area of 700,000 square miles. The glacial flow rate in Greenland has doubled in the past 5 years. And as you can see from the images, the amount of meltwater on the surface of the ice in the summer has increased rather dramatically just over a decade. The air temperature over the last 20 years has increased by 4 degrees Fahrenheit. Now, if all the Greenland ice melted, it would raise global sea level by 23 feet, and most of the major cities of the world would be underwater. Now, that's not going to happen on the timescale of a decade or even on the timescale of a century. But the melt rate, as you'll see in a minute, is going up dramatically, and it's adding to sea level rise. Another example of foreshadowing is the Arctic sea ice. Now, this is different than the ice on Greenland, which is on land, and so when it melts, it raises sea level. Melting ice that's floating on the surface of the ocean does not raise sea level. When you have your cup of iced tea and you've got ice cubes floating around in it, as the ice cubes melt, the water doesn't flow over the side. Ice floats because it's less dense than water, and so when it melts, it becomes more dense and the water level remains the same. So the melting sea ice in the Arctic is not raising sea levels. But what it is doing is reducing the reflectivity of our planet, because ice is highly reflective, and exposing more water that is better at absorbing energy from the sun, and therefore leading to that positive feedback loop I talked about. A raising temperature leads to a raising temperature. Here you see in the yellow outline an image of the Arctic sea ice, averaged over the period 1981 to 2010, during which global warming was rapidly accelerating. And yet the picture is from 2016, the warmest year on record so far, where you see nearly half of the ice disappeared in one summer. Here we have the IPCC predictions of the amount of Arctic ice we'll see. You see it's gone from about nearly 7 million square kilometers of ice in the 1960s and 70s. As global warming has kicked in, it's been declining by more than 50%, down to about 4 million square kilometers now. And it will continue to decline on any scenario, even one where we curb dramatically our CO2 emissions down to a level of 2 million or less. And in the less optimistic scenarios, it disappears essentially completely in the next 30 years. Now, you might have heard that, yes, the Arctic sea ice is melting a little bit, but the sea ice around Antarctica increasing, so it's sort of a wash. Well, indeed, it's true. Back in the 90s and the early 2000s, the amount of sea ice in the ocean around Antarctica, again, we're not talking about the ice on the continent, but the ice in the ocean floating near Antarctica, was increasing very slightly. Here you see the annual cycle of melting and freezing and a slight trend upwards. But that was then, and this is now. Here are two images from the tip of the Antarctic Peninsula taken in February of 2020. The one on the left on February 4th, the one on the right just 9 days later, February 13th. You see the huge melt ponds forming on the surface of the glaciers and much of the snow and ice having melted away in just a little over a week. How did this happen? Well, because of this. On February 6th, the temperature in the Antarctic Peninsula was 64.9 degrees Fahrenheit. It's the same temperature it was in San Francisco that day, and this is Antarctica. So while the Arctic sea ice has been going downhill over the last 50 years or so, and you see the minimum in 2012 and 2018 is nearly as low, the Antarctic ice was slightly tilting upwards until that warm year of 2016, when it plummeted such that the net ice on the surface of the Earth, and that's the total we need to use when we calculate how much solar radiation is reflected by sea ice, has plummeted over the last few years. Finally, another example of foreshadowing is forest destruction. Everyone's heard about the burning of the rainforest in the Amazon, but this is also going on in equatorial Africa and in Southeast Asia. Trees are being burned and cut down. Burning is the combining of carbon with O2, oxygen from the air, which yields CO2. So the burning of a forest adds CO2 to the atmosphere. This is happening not just in the tropics, but also in mid-latitudes, as you know, from the fires in the American West, and at very high latitudes across Canada, and in particular in Siberia, where hundreds of thousands of square kilometers of forests have gone up in flames. This has two effects. It adds CO2 to the atmosphere directly, just like burning fossil fuels, and in 2020, the amount of destruction was up by 12% over just the previous year, and 2.5 gigatons, 2.5 billion tons, or 7% of our total CO2 contribution came from this source. But it also decreases a sink of carbon. That is, trees suck carbon dioxide out of the air, and if the trees aren't there anymore, then we don't have that buffer against the increasing CO2.